Hello, class. I'm coming to you today with section 5.3, looking at Riemann sums. We'll talk about that briefly and focus majority of our attention on definite integrals, section 5.3. So I'm going to begin with sharing my screen. So here we have the notes, okay? A couple of objectives there. And of course, this does list it as chapters, but remember, chapter 5 is module 4, okay? Read the chapters and numbers and kind of ahead as far as models. All right, so we looked at some summations, a few limit summations in 5.2. We didn't call them specifically Riemann sums, but that's what they were. So we have a definition here for Riemann sums, which then brings us to the definition or gives us the ability to define the integral, the definite integral. So here, definition of Riemann sums, let f be defined on the closed interval AB and let delta be a partition of AB given by where A is just some endpoints, some values, and of course where A is smaller than B, and where delta x is the width of the ith subinterval. Okay? If C sub I is any point in the ith subinterval, then the sum is called a Riemann sum. That the sum from I equals 1 to n of f at C sub I times delta x is called a Riemann sum of f for the partition of delta. And it may not mean a whole lot to you right now, but I believe it will in just a second. So now let's take a look at the definite integral, how these two are related. So if f is defined on the closed interval AB, and the limit of Riemann sums over the partitions delta equals this, it exists, then f is said to be integrable. So in other words, if the limit exists, the limit of the Riemann sums exists of f, then we're saying that f is integrable. So the limit of the Riemann sums is equal to the integral of f of x from a to b. And so I want you to recall back when we were looking at differentiation, we started off with the limit process, and we used the limit process to define differentiation. Now look at how we're looking at the limit of Riemann sums to define integration, or how limits and integrability are related, as well as limits and differentiation. So that links differentiation and integration as well, the two branches of calculus, that links them together. So if a function is continuous, that also does imply that it is integrable also, that it can be integrated. So we're going to look at some examples. I've got some homework problems that we will most definitely look at, and I think I may actually start there because that first homework problem to me might be a little easier than the example that I was going to start with. The homework problem number 1 on the homework might be where we start. I think it is. And what we've got here on number 1, it simply says evaluate the definite integral by the limit definition. Okay? By the limit definition. So I'm going to write down the problem first, and then we'll refer back to the notes when we need to evaluate or to finish them up, the definite integral. My number 1, the ID problem, I believe they all should stay in the same order, but just to make sure, the ID for my number 1 is 5.3.005. Okay, and this is section 5.3. Okay. All right, so our integral is from 1 to 6 of 6 dx. And dx is just your integration variable, or it just tells you what you're integrating with respect to x. Okay. All right, so according to the rule, we're going to, the definition of integral, the definite integral, we're going to find the sum of this function using this definition, the sum of Riemann sums f at c sub I times delta x sub I. Okay? Now, a few things we have to find in order to apply this. So, our function is just 6, so the function that we're given is just y or f of x equals 6. You could call it y or f of x. Okay? So, that's our function. So, now let's find c sub I. C sub I, and we're going to also find delta x sub I. Okay, and we've got to partition the interval from 1 to 6. So C sub I will be A, and this C sub I is just the right endpoint. Okay, that was discussed at the beginning of the text. So you may want to, even though I'm giving you some notes, you still may want to look at your text. Make sure you look at the examples there. Remember, we're limited on time, so the text will give you more details. Okay. So C sub I is how you evaluate the function at the right endpoint. C sub I represents a expression for the right endpoint, and it's A plus I times delta x. Okay, so we do need delta x actually first, and that is simply d minus a over n. Delta x is just d minus a over n. Okay, so let's get delta x. So delta x for this particular problem, b minus a over n is just 5 over n. Okay, we got our delta x. Now we're ready to write our expression for c sub I. A is 1, so 1 plus I times 5 over n. So c sub I equals 1 plus 5I over n. This one off, circling that one. Okay, so our function f of x equals 6 or y equals 6 is the sum is equal to the integral from 1 to 6 of 60x is equal to the sum of f from 1 to n of f at 1 plus 5I over n, just replacing the ci with that, times delta x, or delta x of I, which is times 5n, 5 over n. I've got the function at c sub I times delta x of I. Okay, keeping that going. So this is just the function at this particular value, where our function is just a constant. So that's just 6 times 5 over n. So the sum from 1 to n of 6 times 5 over n equals the sum from 1 to n of 30. 6 times 5 is 30 over n. And then I'm able to pull that n that's on the bottom. I can pull that away from the 30 and put that in front. And then I just have the sum of a constant. And remember, we know how to deal with that. So 1 over n, remember those formulas, those summation formulas from 5.2? The summation of a constant is just that constant times that top n, times that top limit value. So 1 over n times 30 n. And the n's just cancel each other out. So that's just 30. We just have 30. Okay. All right. Let's see if we can find us another one. We've got, we've got number 2 that we can look at. By looking at the limit definition. Yeah, we'll look at number 2. Oh yeah, yeah, we'll definitely look at number 2. It's a little different. It's actually Evaluate this, so it's the same direction. Evaluate, put it down, sorry. Evaluate the definite integral. And excuse my pauses sometimes. When I'm pausing, when I'm looking at something, I'm trying to figure out the best examples to work. Trying not to do the exact same type every time. All right, so here's one from -3 to 4, x dx. And then let's see what other ones I want to look at. I feel like I might should have done that one. That one's really, yeah, let me do a different one. Let me do one that may be a little bit more complex, just so you can get a good, well-rounded picture. All right, so let's look at number 4 instead of number 2. Let's look at number 4. It's a little bit more complex, and then we'll move on to even something else here in a little bit. All right, so same direction. It says evaluate. I wanted to do this one because it wasn't just an x, it was a 9x squared, so it has a little bit more on it. Evaluate the definite integral. By limit definition. And of course, you know, there's going to be a faster way to do these definite integrals in just a little bit, especially when we get to 5.4. But I'm just showing you the way to evaluate it using the limit definition right now, since that's what it says. All right, so the actual definition from 1 to n, the summation of f at c sub I times delta x sub I. And remember, delta x is b minus a over n, and c sub I is the endpoint a plus I times delta x. Okay? All right, so let's first get delta x. So delta x is 9 minus 1. Remember, this is a, this is b. 9 minus 1 over n, which is just 8 over n. Okay? Then c sub I, that's a, which is 1 plus I times delta x. So a is 1 plus I times delta x. Delta x is 8n, or 8 over n. So c sub I is 1 plus 8I over n. Okay? So we got that. Now we're ready to actually apply this limit definition to our function. Our function, f of x, is 9x squared. Okay? So it's actually quadratic in this case. The last example was a constant function. So we've got the sum, so I'm applying this right here. The sum from 1 to n of f at c, which is 1 plus 8I over n, times delta x sub I, which is just 8 over n. So I'm going to take the function, and wherever I see x, I'm replacing it with this. So this would be the sum from 1 to n of 9 parentheses, because it's 9x squared. So 9, the x is getting replaced with this. 1 plus 8I over n squared times 8 over n. Okay, so that's what we have right now. And so at this point, we, of course, have to really clean this up. So first thing I'm going to do is take this 9 and this 8 over n and just make that 72. 9 times 8, 72 over n. I'm going to pull it out front. And then I still have this sum from 1 to n of 1 plus 8I over n squared. Okay? So this I have to expand out. So 1 plus 8I over n times 1 plus 8I over n. So I have to FOIL this basically. 1 plus 8I over n times 1 plus 8I over n. So if you're foiling this, if you're using the FOIL method, then this becomes, we got the sum here from 1 to n, but this becomes first times first, you still got the 1. The two middle terms, the inner term, you got 8I over n. The outer, you got 8I over n. So you got 16I over n. The outer and inner products come together to give you that middle term. And then last times last, 8I over n times 8I over n. So you got 64I squared over n. Actually, over n squared. The n's are squared too there. Okay. So now we are working to try and clean this up, try to write the summation for I differently. So think about it like those summation formulas back in 5.2. So think about it. All of these have their own little summation, okay? So this is just with the sum of, like, still got 72 over n out front. But this would be, let me go ahead and write it. That way we're not confused. So the sum of 1 from 1 to n plus the sum of 16I over n plus the sum of 64I squared over n squared. Okay? Now you can see how they all have their summation. So we're going to apply the summation formulas because I can pull that 64 over n squared away. I can pull that 16 over n out front here as well. Now the summation of a constant would just be that constant times n. So this is just 72 over n still out front. This is just 1 times n or just n. This 16 over I will come out front, and the summation, 16 over n will come out front, and then the summation of I from those formulas is n times n plus 1 over 2. That's from 5.2, the summation of I. And then here, the 64 over n squared will come out. And then the summation of the I squared, that is also a summation formula, and it is n times n plus 1 times 2n plus 1 all over 6, according to that formula, according to the formula, okay? So at this point, we're just trying to clean this up. I mean, basically. Let's see what we've got, and then we'll finally be able to take the limits as n approaches infinity. We'll be able to finally see where this is headed, okay? So remember, it's the limit. It's equal to, the integral is equal to the limit of the Riemann sums, okay? And I actually, let me make sure you're clear on that, what I'm saying here. Yeah. So I don't have the limit out front. I don't have the limit written out front like I should have. But just understand that the integral is equal to the limit of the summation, okay? So the integral, and I probably need to clean this up some more. Yeah. Okay, so let me do that. Too much to leave like that. So let's clean that up some more. All right, so we've got the 72 over n times that n. That's going to wipe that out. Before I do that, though, that's going to wipe the n out. before I do that, let me clean up what's inside here, because the n here and here on the top and bottom should cancel to where I just, oh, and then here the 16 over 2, that's going to just be 8 there. Computer's frozen again. All right, let me try this again. I'll share my screen again. Keeps freezing up. Still frozen. Hold on one quick second. I'm so sorry. Been doing this lately for some reason. Not entirely sure why. This is just technology. Okay, there we go. Not frozen anymore. All right, so what I was trying to do was just clean this up in here before I multiply through with that 72 over n. So that 16, that 2 will reduce, that n and n here will reduce. So right now I have 8 and I have n plus 1. Okay? And then, of course, in a minute I'll have that multiply through. Keep going. The 64 and the 6, I know have 2 in common. So 2 will cancel out of here, leaving with 3, and 2 will go here and leaving with 32. One of these n's in that square will cancel with that one there. So right now I've got 32 n plus 1 times 2n plus 1 over 3n. Okay? Excuse me, I had to get a drink of water. Okay, so now let's multiply through here. Okay. So right here, those n's will cancel. So it'll just be 72 for that first term. Here, I'll have 72 times 8 times n plus 1 and then over n. So 72 times 8, let's go ahead and just see what that is. That's 576. So I've got plus 576 n plus 1 over n. Okay. Then 32 times 72, let's see what that is. 2,000. That seems kind of big. Hold on. Oh, and I'm going to divide by 3. That's right. So yeah, because I got the 3 on bottom. So 72 times 32, and then divide that by 3 gives me 768. And then I've got times n plus 1 times 2n plus 1 all over n, and n gives me n squared. Okay? So now we're going to say that the integral from 1 to 9 of 9x squared dx is equal to the limit as n approaches infinity of all of this Riemann sum. Sorry, let me see that up. Of all of this, the limit as n approaches infinity, this integral will equal that. So we just simplified the Riemann sum, and now we're taking the limit of the Riemann sum as n approaches infinity. So this is 72 plus 576 n plus 1 over n plus 768 n plus 1 times 2n plus 1 all over n squared. All right, now as n approaches infinity, let's see what happens here. So we got to think about those indefinite integrals. Remember back when we were looking at as n approaches infinity, what happens to this basically is what we're trying to focus on. So this is 5072. Okay. As n approaches infinity, so as this gets bigger and bigger and bigger, and dividing by as this gets bigger and bigger and bigger, basically that cancels out and leaves us with 576. And then here, we have as n goes to infinity, hmm, 768, then this ends up being like infinity here. It's bigger and bigger, and so does that. But that's times 2 there. But this ends up being plus 1536. So the 768 and that 2 end up giving you 1536. These cancel out at the end. So 72 plus 576 plus 1536 ends up giving us 2184. And like I said, there will be a shorter way to do this in just a little bit, where you won't have to do the definition for the Riemann sums and all that. Okay? Let's see what else we've got here. What the other problems look like. All right. Picking back up here with a few notes. We'll look at more problems here. The definite integral as the area of a region. So we can also define the definite integral as the area of a particular region under the graph, bounded by, of course, the graph itself, the function itself, the x-axis, and then your vertical lines created using your endpoints. So if you were looking at this function and you were to you wanted to determine the definite integral of this function from a to b, you're basically looking for the area of this function, the area under the curve of this function from a to b. Okay? Here's another picture, similar. Here's the function itself. And you can see that we could find, or we could rather, we could find the area under the function from 0 to 4, for this particular function. Okay. So when we look at definite integrals, keep in mind that most times we use x, but you could use another variable. It could be replaced by another variable without changing the value of the integral. So the dx or dt is just kind of called the dummy variable. It's just telling us with respect to what variable we're integrating. Okay, so we're integrating x plus 2 with respect to x from 0 to 3, integrating t plus 2 with respect to t from 0 to 3. You will get the same value for that integral. A couple of properties for definite integrals here. Because we will look at some definite integrals where we'll apply a few properties before we get to 5.4, where we actually see the shorter cuts, applying the rules a little more. You don't have to use the limit, really, once you get to that point. So here it just says if f is defined at x equals a, then a to a would just be 0. The function evaluated, or the integral of the function from a to a would just be 0. If f is integrable on AB, then the integral of f of x from b to a is equal to the opposite of the integral of f of x from a to b. Okay, so it's just where the endpoints were flipped and you made it negative. Okay. And then we've got some properties of definite integrals. If you've got some c contained within the closed interval AB, then you can actually break the definite integral up into 2. For example, the function integration of the function from a to b is equal to the integral of the function from a to c plus the integral of the function from c to b, still equivalent to that whole integral. If you've got a constant multiple times the integral of a function, pull that constant multiple out front and integrate it. And if you have a sum of terms of functions, you can give each part or each term its own integral. Okay? All right, and then this is just preservation of inequality, just saying that if some function f is smaller or lower than g, less than or equal to g of x, then the integral of it should still also be less than or equal to the integral of g of x. Okay? So there, I want to look at more homework problems now and kind of focus on that. Shouldn't have to go back to the notes, I don't think, at this point. All right, so let's take a look at some other problems where we're doing some different things. So you're going to be doing about 8 or 9 of those problems where you're evaluating the limit or evaluating the integral using the limit definition, what we just did. All right. So let's look at now where we are writing the limit. You got a few of those. I don't think we'll have any trouble with these. This is number 7, I believe. The ID is 5.3011. So here it wants us to write the limit, this limit as a definite integral on the interval a to b, where c sub I is any point in the ith interval. So if you want to express this limit as an integral, then it would be from -8 to 3. Remember, c is just some point on the interval within the function. So then you're really supposed to think of that as just x when you're writing the actual integration or the actual integral. From -8 to 3, so 3c sub I plus 3 delta x, that would be the integral from -8 to 3, 3x plus 3 dx. Okay? And of course, dx is just you telling to what variable you're integrating. Okay? Here's another one. It says write the limit as a definite integral where c is any point in the ith subinterval. So we've got 8 to the negative c sub I sine c sub I delta x sub I. So this would be the integral from 0 to pi thirds of 8 to the negative x times sine of x. And I may not even need to use it around that. And then dx. That is. So 8 to the negative x sine of x dx. Okay? So just writing there. More writing. Supposed to, this time, it's the function is given, and it says write a definite integral that yields the area of the region. It says do not evaluate the integral. So again, you're just writing the integral. So you're given the function. I'm sorry. You're given the function, and you're asked to. And this, the idea of this problem is 5.3016. The problem itself, I can't tell. I'm sorry. So the integral would be 6 minus 3x dx. And that is from 0 to, oh, okay, we're supposed to look at the picture. From 0 to 2. 0 on x, so the function starts here, to 2. Because it's what the x value is. So, or where the x starts. So the graph begins on the y-axis, which means x has to be 0 there, and it ends here where x is 2. Okay? Looking at the graph to figure out what your endpoints are. Here's another one. The function is 25 minus x squared, and then here's your picture. The x values go from -2 to 3, it looks like. So that would be the integral of f of x, which is 25 minus x squared, from -2 to 3. Okay? All right, so let me see, after those problems, are we evaluating any? And you got a few at the very end where you are asked to sketch the region whose area is given by the definite integral. Okay? So here it says sketch the region whose area is given by the definite integral. So this starts out as just a constant. And so I'm going to go ahead and tell you. The next section, we'll actually see a shorter cut way to do this, to do these integrals. I'm going to go ahead and just mention it now because I actually think we saw it a little bit in one of the early sections, like 5.1. So that way you don't have to try to apply the limit to just figure out which of these graphs is the correct region for that integral. So think about it like this. You're integrating a constant, okay? That becomes a linear term. So you're integrating a constant with respect to x, so the integral of 6 with respect to x becomes 6x. If you think about the rule for, I guess you can call it the back in 5.1, I don't want to say the power rule, but kind of. So the integral of 6, the integration of just 6 becomes 6x. Okay, so the function is actually 6x. So the integral from 0 to 9 of 6 dx is equal to 6x evaluated from 0 to 9. And then we'll shade, of course, the area under that graph. So 6x you can actually look at in your calculator, or you can, you can look at it in your calculator, I guess. It says use geometric formula to evaluate the integral. You can look at it in your calculator. Put the function 6x in the calculator, I guess, if you want to. And then just hit the graph. Use my calculator. I just see this. Yeah, then just hit the graph, I guess. Yeah, I guess. Okay, so, yeah, it's not really. Yeah, it's not really what I want to do. Okay, so the graph up here, more so look at, don't look at the integrated function, because that's not really what we're doing up here. The graph that is the correct answer is going to be the graph of the original function that you're given, just the constant 6. And we know 6 is a horizontal line. The graph of 6, just the constant 6, f of x equals 6, is just a horizontal line through 6, through y equals 6, or at y equals 6. So that's where you can see that this is the graph. Now, from 0 to 9 is where you shade underneath, and you want to find this area. So then getting that area, you don't have to integrate this at all. Getting that area, you can use base times height. as a geometric formula because it's just a box. It's just a rectangle or just a box. So base times height, we can say this height is 6, this base is 9, so 6 times 9 gives us 54. Okay? I was making it more difficult than I had to. This is another one. So this problem really does focus on, like I said, just evaluating the limits. I may try to find one more of those, but then again, I may just move on to the next section with a new video. Oh yeah, let's look at these, a couple of these. So number 17 and 18, those last two problems in this section, ask us to evaluate the integral using some given values. Excuse me. So it's like you're using some properties. So this is number 17. Sorry about that. It's ID is 5.3037, if that helps. All right, so let's look at this one. So we're given the integral from 4 to 6 of x cubed is 260. The integral from 4 to 6 of x is 10. And the integral from 4 to 6 of just 1, so there's nothing there, understood to be a 1, is just 2. And we want to use all that information to evaluate the integral from 6 to 4 of x cubed. Take a look at what happened. We reversed the interval, the endpoints. So we started out with this given piece of information. The integral from 4 to 6 of x cubed is 260. So the integral from 6 to 4 of x cubed is equal to the opposite of this one, that first one. The opposite of 4 to 6 x cubed dx. We know that is 260, so the opposite of 260 is negative 260. So this integral from 6 to 4 of x cubed would be negative 260. This one, you are given some information. You're given the integral of 4 from 4 to 6 of x minus 19 dx, and you're asked to evaluate that using these pieces of information. So we're given the integral from 4 to 6 of x cubed, the integral from 4 to 6 of x. So let's do this. Let's break those apart. X minus 19 give each its own integral. Okay. Now, yeah, let's do it this way. Keep in mind, write that again. This 19 is a multiple, a constant multiple. You can pull that out front. And so you got the integral from 4 to 6 of x minus the integral, I pulled out the 19 out front, from 4 to 6 of dx. So this part, the integral of x is 10. 4 to 6 of x dx, that's 10, that's what we're given. And then we've got minus 19 times the integral from 4 to 6 of just dx, which is just 2. So 10 minus 19 times 2 gives us a negative 28. Okay? And again, that was number 18. So again, the main part of this section is limits. So applying the limit definition to find those definite integrals. But this next section that we're going to look at, I think will actually even make answering some of those problems easier. I know it sounds weird, but sometimes in math we learn the more technicalities of it before we get to the easier way to do something because they want you to understand it first. So yeah, that's what we're looking at. All right, so that is I'm not even sharing my screen all that time. Oh my God. Wow. Oh, wow. Let me see, what can I do other than redo the problem?